Imagine we have a robot. Now, I'm saying imagine because we don't actually have a robot, so I'm using this car instead. After all, for what we want, they're basically the same thing. They both have four wheels, take an input, and turn that input into an output. Now, let's say that at the press of a button, we want our car to go at a constant speed. We want it to stay there even if it goes over bumps. How do we do that? Well, with control theory, of course. Control theory, as the name suggests, deals with control of systems, like our robot car here. It works to make them more stable, more accurate, and more quick to adapt to any unforeseen disturbances. Now, there are two main types of control. The first type is called feed-forward control, and it works to account for errors before they happen using a combination of calculations and modeling. Now, feed-forward control is great for things that can be easily predicted using these calculations and models, like the amount of power that needs to be constantly fed into the motor in order to overcome the force of friction between the wheel and the floor. However, when it comes to things like going over bumps, feed-forward control doesn't do so well, because those are unforeseen disturbances that can't be accounted for beforehand. In order to deal with going at a constant speed while going over bumps, we need a different type of control. Feedback control is what works to help the system adapt to any unforeseen errors. Here's how it works. The system outputs sensor data every 20 milliseconds or so. That data is then fed back into the controller, which uses it to help calculate its next move. The controller then gives that information to the system, which moves and outputs more sensor data, repeating the cycle all over again. One common type of feedback control is what's known as PID, or proportional, integral, and derivative control. This algorithm uses the error, the sum of the errors over time, and how fast the error is changing in order to make the system's movements smooth, accurate, and quick to adapt and go back to normal after encountering a disturbance. Now, let's go back to our car and see control theory in action. Feed-forward control alone is pretty good when you're trying to make the car go at a constant speed along a constant surface, since that's something that can be easily modeled or calculated. However, when the car encounters something unexpected, like a bump, feedback control has to kick in. The sensor has, as usual, been sending data about the car's speed back to the controller. But on this case, when it hit the bump, the car slowed down ever so slightly. And when the controller sees the new, slower data point come back from the sensor, it goes, "Oh no, I'm going too slow," and it tells the car to speed up. The car speeds up, sends out more sensor data, and the cycle continues until the car once again reaches its constant ideal speed. And that's some of the basics of control theory, a complex field that covers everything from robot arms and wheels to machine learning. If you want to learn more, please check out the sources in the description, and thanks for watching.